This video lecture going to be provide information about the basic processing unit as a part 2 under comes module 5 of course called computer organization. In the part 1 we have discussed the fundamental concepts about how these signals are going to be generated with the help of the various hardwares, and with the examples also we discuss. So in this presentation let me see the following the steps as a milestones: the hardwired control signal generation with the help of the combination circuit. Also, how to organize this control unit organization, so that is going to be discussed. So generation of the control signals, how to generate the control signals with help of the technique called hardwired control mechanism. So the other one is called the micro program control signal generation, so that is through the micro routine for branch instruction. So the micro program control, so going to be discussed that alternative technique to generate the control signals as hardware control signals generates. The micro instructions going to be perform some concurrent micro operations. Organization of the micro program control, which program contains the set of micro instructions. So micro instructions with the next address field sequencing organization also going to be discussed. So the partial format for the micro instruction field encoded micro instructions going to be discussed. So coming to this hardwired control signal generation, let me see the component are involved here. So to execute an instruction, the processor must have some means of generating a control signals, which are essential in the proper sequence. That should be in the proper sequence. So two categories of control signal generation: one is called hardwired control signal generation and other one is a micro program control signal generation. So hardwired control signal generation with help of the combination logic circuits going to be exercised here is going to be generates some signals. So the here the most of the design of the architects is going to be decided here. Once it is decided and it going to be a complete package, it going to be fixed here. It is going to be fixed here. And for example, the 8085 have 72 instructions. Similarly, 8086 have 76 or 78 instructions. So these number of instructions are fixed. We cannot add or delete those instructions, which is the hardwired control signal generation mechanism. Whereas a microprogram control signal generation, it is quite alternative and flexible, which may require more time compared to the hardware control signals. So that also is going to be discussed. So hardwired system can operate at a high speed but with a little flexibility. It is suits for high speed computations. So with a little flexibility going to be exercised here. Propagation delay may exist from gates, right? So this it encourages the high speed and more number of instructions, so that flexibility is there. So this flexibility have some limitation, because that every gate delay have that gate delay, it has to be propagated from one gate to other gate. So it depends upon the gates, that is, and also data need to be processed, right? So data need to be processed, and also the gate each stage gate has to be processed in and transfer it. There is amount of delay will be introduced. So coming to the actual point of this control signal generation, that is a control unit organization. So we have instruction register. We have seen in the single bus organization and multiple bus organization in the part 1 lecture. There the IR is a instruction register which the after bringing some data or instruction from the memory through the MDR, and it rushed to the internal processor bus. Once it is rushing into the internal processor bus, and that instruction has to be welcome in the premise of the CPU. So who has to welcome that IR? IR is an instruction register. It have certain number of bits. For example, it is a 8-bit and 2 power 8. 2 power 8 is a 256 instructions can able to identify uniquely. This is going to be identified. If it is a 8-bit register, this is 2 power 8. It is a 256 number of unique instruction going to be identify that. So it is going to be add a decoder. So it will be decode, that is right. So that is a decoder, and the other one we have a clock signal generation, clock generation in order to drive out the timing sequence, right? Drive out these timing signals. We have a control step counter. So control step counter, that is a step decoder. So it is a step decoder. It will try to release a separate timing line signals, for separate each signals will be augmented with the timing signals. So that step counter will be going to be release the timing signals, which help us to generate separate signals for every instruction, right? So every instruction there is a set of signals going to be set of timings going to be released here, right? Set of timings going to be released here. We have external inputs. So that set of external input going to be also inputted to this decoder where it is coming here. So that external inputs may be interrupts, external inputs may be memory function completion. So if any memory related operations are initiated, so those going to be point out here, those going to be consider here for the instructions considering, that is right. So here this external inputs which is outside the premise of the processor, so those some exceptions, some interrupts, so power failure, some high priority interrupts may also come here. So that is a external input we need to be consider. And for example, that as I told, interrupts are MFC, and also the condition codes. So condition codes are majorly flags. So after every arithmetic operations and logic operations, so that results going to be reflect to the sum of the flags. For example, so flags may be carry flag, maybe auxiliary carry flag, Z flag, that is a 0 flag, sign flag, and P parity flag, like that several flags will be there. So those flags also contribute to derive the instructions or control signals are going to be control signals. So the inputs are instruction register has to become, and for that proper timing signals has to be reciprocate, and the other external inputs has to be report, and the condition codes has to be report. So all these 4 type of information has to be amalgamated here. It has to be meet here. So it had to be report at this junction where that is a decoder and encoder. So decoding will be there for instruction register, and counter will be there for step counter, and these information also coded, and all this information is going to be report here. So once it is reported here, and it will go to generate the control signals. Okay, so the control the step decoder, step counter or step decoder, as I told, this is going to be release the control timing signals. So timing signals 1, timing signal 2, n number of timing signals are going to be generated with a hidden source of for this is a clock is connected, right? So the n number of timing signals are going to be generated, and there is a the 2 power 8 bit IR is there, 2 power 8 number of instructions are going to be decoded here. For example, add, subtract, maybe multiply, end, or maybe reset, so on, that different type of instructions are there, which may be arithmetic or logic, so which going to be have here. So those are going to be coming from this IR, and after decoding, so it is coming to this circuit, right? So I hope it is clear from all this respect. So let's assume that the add operations happen at T6, right? T6 and add instructions are ANDed here, and those AND signal will going to be provide released to the outside. So here the control signals are going to be generated. Maybe this is a add, this is maybe a reset, this may be end, this may be add, so that different control signals are going to be generated from this circuit. So I hope it is crystal clear of this control unit organization going to be generates the control signals, right? So one example we given here, T6 and add will be ANDed with and going to be generate the control signals for addition, or it can use for some other control signal generation. We can see one example here, generating the control signals for Z-in, right? So Z-in, you know that it have in the most of the instruction, even in maybe instruction fetching or execution phase, we have seen the register transfer, and also simple example, add R3 bracket, that open bracket and close bracket R3 comma R1. So that instructions we have seen. So there Z-in is involved most of the time. Whenever we are doing some addition operations or arithmetic operations, so that Z has sit immediately after the arithmetic logic unit, so that Z will be get the results, that is. So that is for in order to do so, how this signal is going to be generated. So for example, we can see Z-in is equal to T1 clock pulse is required, right? So this is going to be help us to generate the separate signal for each operation, separate signal going to be each operation. So one is essential, clock pulse T1 is essential, and T6 ended with add, T6 ended with add. Why we can T6 we can ended? So in a add instruction there is a clock pulse 6 also involved, so T6 added, plus branch instruction T4 is there, so T4 dot, that is a branch. So like that, so many clocks are involved in so many arithmetic and logic operations, so those we have added here. In order to finally generate the Z-in instruction, so Z-in instruction, let we see, Z-in is equal to what? T1 plus T6 dot added, means that is a AND operation. So T6 and add operation, so that is a AND operations. To T6 coming from the step counter and add operation coming from the IR. So both they meet here and they are going to be ANDed. So ANDing will be generates that signal, and one more is the T4 and branch. So branch instruction is required a clock pulse fourth one. So those will be get ANDed, and all three should have R-ing, right? All three should have add and R-ing will be taken place. So completely here we can see Z-in instructions control signals going to be generate. So here Z-in control signals going to be generate. So I hope it is clear. So T1, T4, T6 and branch instruction, add instructions, all those also using Z-in instructions. So that's why we have listed all those wherever Z-in involved. So this complete mechanism to generate the control signals for Z-in. Similarly Z-out, similarly the PC out, PCN, MAR out, MDR out, so on that. So for all those is possible to generate the control signals. So this, with help of this hardwired control signal generation, so the complete mechanism is enabled to understand with help of this Z-in one simple example. Similarly you can try some other example. So that is end control signal how will generates. So AND will be generate, so add will be there at T7, right? So add will be there in the T7. So previous it was T6, so it may be T7, T5 it involved in the branch, so branch, and T5 is a not set flag, and T4 set not flag, and also complete one is ended with a branch, no branch. So like that, several these signals involved when generating the control signals. So all those we can list it. In other words, end instructions, end signal, wherever it is available, if you are able to write this kind of control signals, there it may be required in the end, it may require a reset, it may required in a branch, add, subtract, so on that. So all those we can list them, and similarly we have list them and it will augmented here in the end. Let we see further this is. So T7 and AND will be ANDed here. T7 and add will be ANDed here. Similarly T5 and no flag will be ANDed here. So ANDed here. So similarly we have T4 and N, and that is multiplied with the branch, right? So that is augmented here into AND gate. So T5 and branch, so that is augmented here. So complete all these we need to be OR, then we are able to get a AND signal. So then we are able to get a AND signal for here, that is. Let me further hardwired control signals. It is a fast because control signals are generated by combinational logic circuits, so they are basically fast. So delay in generation of the control signal depends on the number of gates. So gate delay is a matter here, because it has to be propagate the processing of data, for which it has to be passed through the several gates. So that gates also may have some delays. So it has greater chip area but less chip area is used here. So greater chip area is available, but very less chip area is used here. So the disadvantage of this hardware control mechanism, so in case more control signals needed, design of control unit become complex. So for simple control signals, the design is may not be become complex. So modification or addition of control signals is difficult here, because it is a design by the architects, it is fixed, and it is implemented. So we cannot modify further or add our own instructions. So that is difficult to correct the mistakes in the original design. So the design might have some problems or pitfalls, so those we can carry out. We cannot avoid them, or we cannot delete, we cannot remove, right? Because it is a fixed architecture. Hardware is a fixed architecture. Most of the Pentium processor, most of the desktop systems there follow the hardwired control signal generation mechanism. So coming to the other alternative one is a microprogrammed control. So what are the disadvantages? We have seen that so more control signals is required. It is become going to be design is going to be complex. So the design is already done, then we cannot add any instructions. So that the disadvantage we have seen in the hardware controls. So those it may be possible to overcome here. So all instructions in a program are one or more set of concurrent micro operations. In a program, set of operations will be there. So that is a micro operations. So those have concurrent mechanism. Inbuilt concurrency is there to execute them. Each have specific set of control lines. Each have micro operations have control lines. Those will cause and activated to micro operation take place. So activate and they will cause to take the micro operations. So control signal selection and sequencing. This signals selection and sequencing information is stored in a ROM or RAM. right? Read only memory or random access memory. So this will call as a control memory, right? So control memory will call it as a control memory. So that will be contains the set of control signals or sequences there, right? So overview of that microprogram control, we can see control signals are produced by a program which quite resembles to machine language programs. So machine language generates also, no? So similarly these also control signals as a similar to the machine language. Control word, so that we have stored control memory. We told that control signals sequencing and selection stored in a memory, so that each row or each row we call a control word, right? So that is a set of control signals are there in a control memory. So we can drive out each one in the sequence, so called as a control word, right? What is a control word? That is a single control sequence control signals stored in the memory, so that is a control word. Micro routine, so the set of control words or control signals is put it in the basket or routine, that is a micro routine. So micro instructions, each one is a micro instruction, that is a control word represents that micro instructions. Example, let we see micro instructions. So control signals for add R3, that open bracket and R3 and close bracket comma R1 is nothing but add the contents of the R3 to R1. So it is a memory read operations. So first we have to read the memory R3 and bring the data, and that will be act as a data for addition. So let we see how to write a micro control signals, right? Control signals. So micro instructions are, what are the micro instructions we observed in the previous discussion, that is a part 1. So PC in, program counter in, program counter out, MAR in and read operation, MDR out. So IR in and Y in, right? You have seen, no? Select 4 or Y, add Z in, Z out, R1 set of registers are there, R1 out, R1 in, so R3 out, so on, wait for memory function completion and so on. Several control signals we can enlist here. So those are micro instructions, right? So those are micro instructions. So let we begin. So one example we have seen in the previous discussion. So that is a first step is going to be how, that is PC out, MAR in and read. PC out, MAR in, read, select 4, add, comma, Z in. So I have followed that. Is what is a PC? Program counter. Program counter holds the address of the current instruction. So this address will be have here. So that address will be keep in MAR. So read, and read means we direct to memory, ask them to read that what is that this contents of the PC is there. So that's supposed to be this instruction, right? So select 4. In the meantime the processor is that memory is busy, no? So processor free. So in the meantime we advance the program counter so that it will point to the address of the next instruction. How we can advance? We can increment by 4. So since we assume that 32-bit instruction, so the 4 byte we need to be advanced. Select 4, add. What is a add? Add means contents of the program counter will be added with the 4 value. So the 4 will be added to contents of the program counter. So the PC out is there now. So due to that PC out, the other variable, that B, you can recall that ALU circuit. So ALU have two input A and B, right? So B connected directly the bus and A connected to via mux through that select 4 and Y register. So that is coming, that is what is called the select 4 data 4 will come enter into the ALU, then B will receive, what is a B, that other B connect to the bus, no, it will receive the program counter value. So that program counter value will be added with the 4 and place in a Z in, right? So Z in is it is at the gate of the what is called ALU, no? So there Z in register is there, so Z in will be welcome that. So this we have seen in the previous discussion. Okay, so now for this how can generate the micro instructions, right? So let we see micro instruction. So that is a PC out. PC out is a here, no? So this would be 1, and MAR in, where is a MAR? So MAR is 1. So read is 1, read is 1. Select 4, so of 1, and add is 1. Z in is 1. So all other are 0, right? So whatever 1, 2, 3, 4, 5, 6. So these are all will be 1, and remaining will be 0. So that we need to be full, that is. So here PC out is 1, MAR is 1, read, and Y in, so that is Z in, right? So select and add will be there. So Z in will be there, right? So Z in will be there. So all other will be 0, except that is what is called, okay, MAR, okay, that is correct. So except those will be 0. So I hope it is follow how to generate the micro instructions. So for example, this is a add indirectly R3 to R1. So for we have seen the control signals. So for the corresponding control signals, we are observing a micro instruction. Wherever these are there, we write 1. So those who are not enlisted here in the control signals, so for them we have to write 0, right? Similarly, you can see one more example. So that is after Z in, so Z out and PC in. So the advancement of the program counter happen, so that we can store back, so that PC will be advanced automatically. So Y in, copy to give, can Y in, and wait for memory function completion. Why? Because in the previous clock we inserted the read operation, so that's why we should get a green signal from the memory. So because it is located outside the processor, no, so that processor has to be get a opinion, because that heterogeneous speed, no, processor it may performing or sometimes slow. So that's why we should wait till get a clear green signal from the memory related devices. So then only we can proceed. Okay, anyhow, for this, what is the micro instructions we can see. So Z out will be 1, PC in is equal to 1, Y in equal to 1, wait for memory function will be 1. So remaining will be 0. PC in will be 1, and Y in will be 1, and what else? So Z out will be 1, and wait for memory function will be 1. So remaining will be 0. So second micro instruction ready. So next we have MDR out and IR in. Only MDR out and IR in will be 1, remaining will be 0. So MDR out and IR in, so remaining all are 0. So this third steps will provide the third micro instruction. So this completes the instruction fetch. So now we are able to understand what is that instruction. After fetching, we can able to, okay, let's proceed for the next one, R3 out, because R3 is the indirect addressing mode, so we need to bring that content. R3 out, MAR in read, right? Putting into the MAR and insert the read operations, through the MAR it go to the memory and read that what is the contents of the R3, right? So that is we can see 3 ones are there. What is that? MAR and R3 read, and what is called R3 out, right? So similarly, so we have R1 out, Y in, wait for memory function completes. So in order to perform this, so it is means that we have to perform addition operation R1 with the contents of the R3, right? So R1 anyhow here, so we can put in the Y. We can recall the ALU, so ALU have two inputs are there, A and B. So A coming via mux entering into the select and Y. So through the Y we can send R1. So previously we have inserted memory operation, so we can say wait for memory function completion. For this, what is a micro instruction? So let we see. So what is the micro instructions? So there is a Y in 1 and R1 out 1, and wait for memory function 1. Remaining will be 0. So similarly, next we have about to finish this instruction completion, MDR out. MDR out means after wait for memory function completion. So we expect the data has to be arrive through the memory bus where that MDR is there. So what is that data? So the contents of the R3, right? Contents of the R3 is there arrived as soon as memory function completes. It understood that, so that data has arrived at MDR. It is stationed there. So now it is stationed there. Then we have to ask them to move out. So MDR out. If you say MDR out, and it will be rushed to the ALU through B, right? Because that is a default gate is opened, right, to enter into the ALU. So that will be run. Select Y. So select Y. Y means what? R1 we kept in Y, no? So R1 in the previous kept. Now we can say both the data are ready. Select Y, it is R1. MDR out is R3. Contents of the R3, right? I hope you following. What is a select Y? Select Y is a R1. What is a MDR out? MDR out is a contents of the R3. So we are planned to add those. No, that is the intention behind to execute this instruction. So these both are get added. So it is add operation. After performing addition, what will happen? So result will be at the ALU. So we have to take that copy and put there. Where we have to put? So Z in, right? So at the Z in we have to put. So for this, what is a micro instructions? So MDR out, select Y, and add Z in, all are 1, remaining will be 0, right? So this next we have, once Z in is there, Z out we have to make it. And what is the plan to store the results at R1, right? At the R1 we have to place the result. So Z out R1 in, Z out R1 in. So Z out is a complete results will be there. So that we are put the copy into R1. So the earlier value of the R1 will be destroyed. So that is a end. So only 3 these micro instructions are there. So we can put there 1, 0, 1 and all those. So this is a complete micro instructions will able to provide for the control signals which you have seen in a yard indirectly R3 comma R1. So I hope it is followed with help of this example. So let me further. So that is a control store, that is a control memory. So we have the instruction register. So as we seen that n bit will be there, 2 power n number of instructions signals going to be generated. So we have a starting address generator, because we have seen the setup micro instruction that will be micro routine. So the starting address of that control store going to be generated. So we have micro PC. So the micro PC will point to the current micro instruction in a control store, right? So current normal PC was able to point the current instruction of the memory, whereas a micro PC going to be point the current micro instruction in a micro routine. So that is a drive by the clock. So clock will be control store will be there, right? Control store is a control memory. So there is a set of micro instructions will be there. So for which the micro PC will going to be point the micro instruction as PC point to the instruction at the memory. So that is a control word is coming from the control word. So PCs have the what is the address of that micro instruction. So that that instruction may be, we have seen the previous T1, T2, T3, T4, T5, T6, T7, so on. That is, so on that example we have seen only 7 clocks were there. In the big program maybe many clocks will be there. So that complete one will be bag. So that control store. So which micro instruction you need, so that is a micro PC will be tells. So there we have to identify, and corresponding micro instruction will be bring out, right? So one function cannot be carried out by the simple organization. It may require more complex operations. So let me see for the branch instruction less than 0. The previous organization cannot handle the situation when the control unit is required to check the status of the condition codes or external inputs to choose between alternative courses of action. So use unconditional branch micro instruction. So for which we can see address of the micro instruction. So that is a PC out, MAR in, read, select for Z in, select for add Z in, that we have discussed enough, and PC out, Z out, PC out, Y in, the wait for memory function. So the program control will be updated, and it waiting for the memory function, because in the previous clock pulse read memory related instruction, the operation initiated. That's why we get a green signal from the memory. So after that we'll get a data at MDR out, and that instruction keep in IR of the CPU premises. That is a held responsible person to hold that the instructions or data which is coming from the memory to execute further. So this complete first 0, 1, 2 steps are related to the fetching phase. Next, commencing the execution phase. So the branch to the starting address of the appropriate micro routine. So the set of micro instructions are there called micro routine. So that is also micro program. So that appropriate address has to be generated to branching, that is. So if we encounter the branch instruction at that micro instructions in the micro routine, if n is equal to 0, the branch to be micro instruction 0. If n is not equal to 0, then we need to be branch taken place. So branch taken means that target address we need to be compute. How we can compute the target address? That is offset field of the IR. So IR format will be tell that is operation operands. So operands may be offset also. The offset field of the IR will be considered here, and that we have to put it to the ALU and select Y, add Z in, right? So select Y means that is a offset will be entered to the Y, and anyhow that current program counter will be roaming in the bus, so that will be entered into the ALU to via B, right? Why both are coming there, and the program counter will be get added with this offset, so that it will be generates the target address. So Z out, PC in, right? So now instead of putting old value of the PC, now latest updated value, that is a computed value, is putting into the PC in. It nothing but the control will transport to the that where that address contains the program counter. So that instruction is going to be fetch here. So that is a end here. So basic organization of the overview micro program control. So there is a control store, allow conditional branch micro program. So that is IR, starting address will be there, micro PC and control store. So the control store will be control word. It may go back to address generation for the next micro routine, right? It will be in the loop, right? So several micro routines there in a micro program. So that going to be generates the every micro routine have starting address. So it jump address will be computed, and the starting address will be going to be generated here. So set up micro routine are in the micro program. So each micro routine have micro PC, right? So that will be going to the starting address generation for every micro routine. So that also receive condition codes and extra inputs. So that is going to be happen, that is. So micro instructions, a straightforward way to structure micro instructions is assigned to 1 bit position to each control signal. However, this is very inefficient. So length can be reduced. Most signals are not needed simultaneously. Many signals are mutually exclusive, right? So at a given stop time they may not required. All mutual exclusive signals are placed in the same group in a binary coding. Partial format of the micro instructions, field encoded micro instructions. So there is a format saved there, F1 001 PC out, 0010 MDR out, 011 Z out, R0, right? 1011 offset out, so on. That is format 1. Similarly format 2, 3 bits format will be there. So PC in will be 001, so on. This is similarly format 3 for 3 bits. So 001 MAR in, MDR in, temp register Y in, and F4 that is 4 bit. So that is a 00 add that arithmetic logic operation, 16 ALU functions will be there. So F5 will be 2 bit 000110, and F6 will be 1 bit 0, that is a select Y, and 1 select 4. So F7 is a 1 bit 0 for no action, 1 for wait for memory function. So F8, so that is 1 bit, so 0 for continue. Further improvement: enumerate the patterns of the required signal in all possible micro instructions. Each the meaningful combination of the active control signals can then be assigned distinct code. There is a vertical organization and horizontal organization of this micro instructions. So advantages and disadvantages: horizontal organizations, long formats, high degree of parallelism are encouraged, little encoding of control information, useful for high operating speed of operations. So vertical one is a short formats, so less ability to for parallel micro operations. It is basically slower operating speed. So microprogram is sequencing. If all microprograms require the only straightforward sequential execution of the instructions except for branches, letting a micro PC rules the sequencing would be efficient. So however, two disadvantages. So one is called having separate micro routine for each machine instruction, which yields a large total number of micro instructions, and huge control store will become. So longer execution time because it takes more time to carry out required branches. Example: add source comma RD destination. So 4 addressing modes: register, auto increment, auto decrement, and index. So these 4 addressing modes are going to be encouraged here. So let me see the flowchart of microprogram for add source to destination, that is R destination instruction. So here we can observe the what we can see that MAR PC, MAR read Z and advance the Z by 4, PC Y, that is a wait for memory function, IR, that will be a MDR out. So we have 003 location. So branch instruction, that is a instruction, that is a R, and we have 3 addressing here: index addressing, that is 161 memory location, and auto increment 141 location, auto decrement, auto increment will be 121. Similarly 11 is a register indirect. So 3 addressing modes will be encouraged. In the case of index addressing mode, so that the PC will put into the MAR read PC advancement 161 162, the PC will be advanced wait for memory function, put into the Y, that is a 163, to ZY, that is a Y plus resource R source. So register source, that MAR, put it Z read, and branch, that is a 170 Ring wait for memory function. So wait for memory function, that MAR, that is MDR, and wait for, that is a 171, and we have from the 142, so that is a auto decrement will be happening. So that is a auto increment will be happening. So here, that is a 121 and 122 locations, so of my control store. So we have MAR, that is a register indirect, the branch will be wait for memory function. So branch 170 wait for memory function, branch 1 wait for all, because all those initiate the memory read operations, so that has to be wind up with help of wait for memory function. Once it is completed, and it has to report to here, that is a MDR into MAR, the read wait for memory function completion. So here we can have, so that branch instruction, so we have register direct, and all those will be help us to compute. So R destination to Y, so Y go to be Z. So R destination, the Z going to be R destination. So R destination will be added with the Y, that going to be placed in a R. So that's going to be complete end. So similarly, that micro instructions are stored here for the same thing what we discussed in the previous case. So that is there. So micro instructions with the next address field. The microprogram we discussed requires several branch micro instruction, need a no useful operation in the data path. So powerful alternative approach to include an address field as a part of every micro instruction to notice that location of the next micro instruction to be fetched. So the address field is going to be added here. So the pros are separate branch micro instructions are virtually eliminated. Few limitations in assigning addresses to micro instructions. So cons are additional bits for address field is required. So due to that, adding address field to that. So micro instructions with the next address field sequencing organization, that is IR, and we have external inputs, condition codes, as we see in the previous discussion also. So we have decoding circuit. So the decoding circuit will be Ring. So we have micro AR. Micro AR is a micro address register. We have seen micro PC. Now micro AR, micro address register will be required. So ControlStore, the AR will send an take an address to ControlStore and bring out the instruction. So once it bring out the instructions, we bring it to the CPU premises, that is a IR, instruction register has to be welcome. So here micro IR will be there. So micro IR will contains the operand address of the operands, offset, everything will be there in a micro IR. So we have that will be next address will be pointing to here to point to the next instruction, micro instruction in a ControlStore. So micro instruction decoder. So this IR we need to be decode. So that will be release the exact operation. So that control signals will be going to be generate. So here we have again going back to the decode. So that micro instructions we can see of the format will be followed. So that F0 8-bit, F1 3-bit, F2 3 bits, and 3 bits for F3, right? So on F4, F5 2 bits, and F6 1 bit. So F7 1 bit. So wait for memory function, no action. F8 is a next address instruction decrement, and F9 is a 1 bit, no action, or R mode, and F10 is a 1 bit, no action, or indirect. So implementation of the micro routine using a next micro instruction address field, we have that 00, that is a first one, and we have a 0th one, and first one we have, and second one, and we have third one, similarly 4th, 5th, so on, that is 121, so 170, and so on, that is. So implementation of the micro routine using the next micro instruction address field. So let me see that R0 to R15, those registers will be here. So decoder will be there, and we have IR, that is R source and R destination, register source and register destination, that is external inputs, condition codes, and decoding circuits will be there. So that is going to be generate the micro AR. So that is a address register, and go to the ControlStore. So that we have a micro, what is this called, micro IR, that is a F1 F2, several formats will be there. You have seen that. So that is pointing. So our destination, and we have our destination will be there. So other control signals will be going to be generated. So this is going to be report here to decoding circuit, and finally it will be close the loop, that is. So from this circuit we are able to understand implementation of the micro routine using the next micro instruction address field. So from this I hope it is clear. Thank you for patient listening of the basic processing unit, which majorly cover hardware control signal generation and their advantage and disadvantage, microprogram control signal generation, and there's the different techniques, and there's a difference between these. We have enough enough information we have seen that basically the hardware control signals are going to be fixed and more complex for the complex more number of instructions we want to add, whereas microprogram control signals are quite easier. We can add any number of instructions which we have wanted. That is flexible but a little time consuming. I hope it is clear, and this material you can get from Carl Homachar and Rancid Jackie et al. Computer Organization 5th edition, Tata McGrail, William Stalling, Computer Organization Architecture, that is a Pearson Education, Pearson Publisher, and apart from this there are also other books are available. Thank you, coordinator, moderator, and subject expert. Any query, post the queries to this mail ID. Thank you one and all.